Now we're going to spend some time talking about geological time, also known as clocks in rocks, timing the geologic record. This story involves a lot of geniuses, maniacs, scallywags, blatherskites, weirdos, etc., and their advances that all tie together to give us our view of how the world has worked in the past and a prediction about how the world is going to work in the future. When we talk about clocks and rocks, we're talking about the discovery of deep time. Geologists have made this discovery over the last few hundred years. And in some ways, this concept goes back about 2,000 years. These clocks can be used to measure the duration of geological processes, plate tectonic activity, for instance, and cycles of the Earth system, the orbital control of the Earth's climate, or the timing of extinction events. Those kinds of things can be derived now that we've improved our ability to look at time in the geologic past. Geologists refer to both relative age and absolute age. An example is you're in a crowd and you're pointing out someone. You might say, I know that guy, he's 48 years old. And I know that guy, he's 28 years old. Those are absolute ages. They're precise periods of time defined for that person. In relative terms, it would be that guy is older than that guy. And you know that because you know something about them or their appearance is a giveaway. Same kinds of things go for rocks. We can look at the ancient geologic record in terms of relative age. The Phanerozoic comes after the Hadean, for instance. Or we can talk about absolute age, the beginning of the Pleistocene versus the beginning of the Holocene. We have those timed to a fairly precise date. Pleistocene, not so much. Holocene, yes. We've seen from the last few lectures the process of sedimentary rock formation, weathering, erosion, compaction, and cementation result in a sandstone. We can put relative age on this, saying weathering occurred first, cementation occurred last, or we can put some precise age on this. So in this lecture, we're going to talk about a number of things. Reconstructing geologic history from the stratigraphic record, how we take stratigraphy from one region and apply what we know from that region to another. We'll talk about relative ages. One thing is older than another, rather than one thing is precisely this age versus another thing that's precisely that age. And we'll talk about measuring absolute time with isotopic clocks. These are radiogenic isotopes that decay at a precise rate. That precise rate of decay or half-life allows us to determine precisely when something happened in the geologic past. So we'll talk about absolute ages and what they have done for our understanding of the Earth. Then we'll go into advances in timing the Earth's system. How knowing when things occur, how often they occur, can be useful for us in the future, predicting when something similar may happen in the future. If it's a problem, how long is that problem going to last? Early on, geologists such as James Hutton and Charles Lyell realized that the features they observed on the Earth's surface were not formed in catastrophic events. That was one leading theory at the time. Big things were caused by big events, and the big event was the flood, Noah's flood. Very upsetting to Kuhn. This flood generated the fossils that we see in the record. It generated the Grand Canyon. It generated all of the major features observed on the Earth's surface. Hutton and Lyell realized that the same thing could happen with small action over a very long period of time. So either one big event or a continuous series of small events both lead to the same observed features. Now, this idea of deep time or immense time was critical for Charles Darwin to more fully develop his theory of evolution. Darwin was a geologist. He was hired to travel on the Beagle to find valuable commodities like silver. He didn't find anything particularly valuable other than his ideas for evolution and deep geologic time, which turned out to be far more important. Now, prior to the development of absolute dating, geologists could only refer to rocks in terms of relative age. These rocks are older than those rocks. Up until the mid-1600s, most people believed that fossils were deposited 6,000 years earlier in the great flood of Noah, when they thought the earth began, or that they grew in rocks. Steno thought different. Steno was a very intelligent man hired by a rich guy, kind of as a personal physician, and in that job he had time to study human anatomy. He would take deceased bodies apart and describe what he saw. He also studied muscles and the way muscles contract, and this led to his insight that muscles don't change volume, they merely change shape. This was a big deal. Shark anatomy also caught his eye when two fishermen caught a great white shark in October of 1666. This is during one of the more recent outbreaks of the bubonic plague, and he took this giant great white shark head to his lab. He dissected it, and he produced this drawing and a report on the internal anatomy of a shark. This was something that hadn't been done before in any rigorous way. So while he was doing this, he noticed that the teeth of the shark looked like things called glossopetrae. These glossopetrae are known as tongue stones, and they were found in certain characteristic rocks. Ancient smart guys like Pliny the Elder suggested that these stones fell from the sky or they came from the moon. Other people thought that fossils grew naturally in the rocks. Now, Pliny, if you haven't heard of him, was probably the first and the last person to know everything there was to know, more or less. He assembled all this knowledge together in a book called Natural History. This book contained every bit of knowledge he could gather about the natural world at that time. He was killed in 79 AD during the eruption of Vesuvius. This is the same eruption that wiped out Herculaneum and Pompeii. So he died in a spectacular fashion. Of course, he didn't know everything at the time, but he knew all the important stuff at the time. Since then, information's been coming in a little bit more quickly, and no one's ever going to get to that point again. Now, assuming that all rocks and minerals had once been fluid, Steno reasoned that rock strata and other deposits were formed when particles in a fluid, such as water, fell to the bottom. The result is horizontal layers. Gravity is going to attract those particles to the bottom of the container or the bottom of a basin. Therefore, Steno's principle of original horizontality states that rock layers form in the horizontal position. Any deviations from this position are due to the rocks being disturbed later. Steno stated another general principle in the same way, or similar way. If a solid body is enclosed on all sides by another solid body, of the two bodies, that one first became hard, which in mutual contact expresses on its own surface the properties of the other surface. So what this means is, in, say, the formation of an igneous rock, the original crystals are going to form without obstructions. They're going to grow in the magma, in that fluid. Any subsequent crystals that grow have to take into consideration that pre-existing crystal that's in their way. They grow around that pre-existing crystal. Just like a rock would grow around a pre-existing shark tooth. Advances in the timing of the Earth system include the development of sequence stratigraphy. A well-characterized sequence of rock in one location is going to provide very strong clues to the sequence of rocks in another location nearby. The closer the location, the more likely they'll be similar or even identical. Chemical stratigraphy uses the chemistry in a rock sequence to define pretty similar things. In this case, the rock might be monotonous. It might look the same for 1,000 feet. Therefore, you might think nothing changed in that period of time that 1,000 foot of rock accumulated. However, when you take a look at the chemistry, you'll see that maybe a lot of things were going on. And you can use a sequence of rocks described chemically in one location to those of another to tie them together in terms of timing. We can use paleomagnetic stratigraphy in a similar way. The positive and negative polarity of the Earth changes not regularly, but it changes often in terms of geologic time anyway. Those changes occur globally. So we can use paleomagnetic stratigraphy to correlate rock sequences on a regional scale to a global scale, if the rock is well preserved. We can use this to clock the climate system. This means ice ages, for example. Up until the 1950s, we thought there were 4 ice ages. Cesare Emiliani came along, the University of Chicago, as a graduate student. He looked at the oxygen isotope record of deep sea sediment and determined there were probably more likely 20 glacial periods, and subsequently it was determined they were about 100,000 years apart. This means that every 100,000 years we go into a glacial episode. Now, we'll get back into this later in the course. Maybe that works, maybe it doesn't work for glaciers, but it definitely works for the climate system in general. We would like to have precise timing of major climate events if we expect to understand why they happened in the past and whether they're going to happen in the future. When reconstructing the geologic history from a stratigraphic record, we need to include principles of stratigraphy. These include original horizontality, first defined by Steno, and superposition. Younger material is going to be deposited on top of older material and will remain in that position unless something happens to disturb the situation. Faunal succession is going to imply more recent fossils will always be found above more ancient fossils. Again, unless that sequence is overturned or disturbed in some way. We can see that illustrated here in Marble Canyon, Arizona. If you've seen photos of the famous Horseshoe Bend in the Colorado River, that's located just to the north of this in Page, Arizona. So what we see here in this canyon, Marble Canyon, is a sequence of limestone that's been baked. And as illustrated here, the younger limestone was deposited on top of the older limestone. There's a mind-numbing gift shop located just off the screen here. It's a very Second Amendment friendly area, if you know what I mean. Now, left undisturbed, the youngest layers are always going to remain above the older layers. This rock hasn't been flipped over, at least as of yet. The mapping of regional stratigraphic succession could be straightforward in some regions, particularly if they're small regions that are exposed to identical conditions throughout the region. We're at one end of a lake versus the other end of a lake, or one end of a marine deposit versus the other end of a marine deposit, or we're in a glacial lake, for example. However, if materials eroded or never deposited, gaps would appear in the record, or would not appear in the record, depending on how you look at it. So along comes William Smith in the 1790s. He noticed that certain fossils appeared consistently in certain rocks while his canal digging company was digging canals throughout southern and western England. This was a period of time when we didn't have railroads yet, so canals were the superhighways for transport of large, heavy materials like grain and rocks and anything else you could fit on a small boat. So canals were the way to go. They were very important at the time. So there were a lot of them being dug. By organizing the rocks in a sequence from young to old, he developed the principle of faunal succession. This is that sedimentary strata in an outcrop contain fossils in a definite sequence. The same sequence can be found in outcrops at other locations, such that the strata from one location can be matched to the strata in another location. That might not seem quite straightforward from the definition, but it will when we look at an example in a few minutes. Basically, more recent stuff is above more ancient stuff consistently. This is a picture of the dynamic individual. This first geologic map was generated in 1815. It's been known as the map that changed the world. For the very first time, we had a predictive capability of what we're going to find if you dig a hole somewhere. Now, prior to that, you dig a hole and you see what's down there. In this case, Smith said, if you dig a hole through this type of rock, you're going to hit this type of rock next. So get ready for it. There's a reconstruction of this map, which looks just like this, not too far from my office in the geology building. It's on the second floor near the dinosaur skeletons, which you'll be able to see when the university is reopened. So this is a map of the strata of England and Wales, published in 1815. And as a result of this map, in part, this led to scientists focusing on collecting, cataloging, and identifying fossils, thereby establishing the field of paleontology. Charles Darwin comes along literally a few years later, studies paleontology, and gets hired as the expedition geologist aboard the Beagle from 1831 to 1836, traveling around the world. That's a pretty exceptional opportunity. So he's a smart guy. He's trained in geology. He's trained in paleontology. He's put on a boat to make England rich. He didn't make England rich, but his travels and his studies led him to formulate ideas that we still hold today about natural selection and evolution. Now, if any person in the past deserves to have a movie made about their life, it's this guy. John Wesley Powell was born in 1834, just after this geologic map was first developed, and Darwin studied paleontology. He was a U.S. soldier, a geologist. He explored the American West. He's a professor at Illinois State University and the director of major scientific and cultural institutions like the United States Geological Survey and the Smithsonian Institution in Washington, D.C. For the most part, people aren't really happy about learning online this semester or last semester. It's a hassle, it's distracting, and lots of pros and cons to it. Now, put yourself in this guy's shoes. He studied geology while he was in the trenches at the Battle of Vicksburg during the American Civil War. He was also studying geology during the Battle of Shiloh, in which his right arm was shot off. So think about that when you're having internet difficulties. This guy was studying while being shot at, and cannonballs were exploding around him. He went on to do some even crazier things, maybe. This is a stamp that was issued in the U.S. depicting his exploration of the Grand Canyon. He was among the first, if not the first person, to travel the length of the Grand Canyon by boat. And you've probably seen video of people doing Grand Canyon rafting these days on giant rafts with huge engines. These guys did it wooden boats, and in his case, with one arm. He's also famous for exploring the Grand Canyon vertically. Climbing up with one arm required that his assistant go up to a ledge first, take off his pants, lower the pants over the ledge. Powell would grab on with one arm. He would haul him up to this ledge, put his pants back on, climb up to the next ledge, lower his pants, and haul Powell up. None of these things killed the guy, somehow. And this is what he studied. The rocks at the rim of the canyon are a couple 100 million years old, whereas the rocks at the base of the canyon, the Vishnu schist, is nearly 2 billion years of age. So there's about 2 billion years of geologic time represented in the sequences of sedimentary rock here in the Grand Canyon.